So we're talking about mysterious fast radio bursts. Mysterious because we just don't know what creates them still. And they are one of the recent astronomical mysteries. So a few facts about fast radio bursts. The new type of recently discovered radio transients. So first one was discovered in 2001, so less than 20 years ago. And they're extremely bright bursts of radio emission. They're very short, few milliseconds, and for reference, a blink takes 100 milliseconds. So they're much shorter than a blink. They're extremely bright, almost as bright as supernovae, and supernovae we know is an explosion of a star. So fast radio bursts are as bright, but they're much shorter than a supernovae takes time. We still don't know what their nature is and what creates them. By now we have 100 events discovered since 2001, and so 100 events have been published. There are more in pipelines that researchers are still investigating. And today they're detected by some of the world's largest and most sensitive radio telescopes around the globe. We know that they're very frequent and expect thousands of fast radio bursts per sky per day. So if you consider the entire sky, you will detect 1,000 per day. Most of them are one-time events, so it's an event that happens and never repeats. But 10 of them were found to repeat. And the repetitions are chaotic. The nature of these sources that produce them is they're all different, so we still don't know if all fast radio bursts come from the same sources, same type of population, or there are few populations of them. And they mentioned they're detected in radio, so in this case it's about 600 megahertz to 1.4 gigahertz. This is an example of one of the largest world's telescopes, Arecibo, located in Puerto Rico, that has detected fast radio bursts. Its diameter is 300 meters, and it's just a surface carved in a crater in the forest. So a bit of the first discovery, it was published in 2007, but the discovery was made in 2001. It took 6 years to, for the researchers to make clear that this pulse is actually of astrophysical origin and not artificial or created by terrestrial microwaves, for example. The scientist named Duncan Lorimer, who is in West Virginia, made this discovery by searching through archival data of pulsar catalogs. So the archival data is something that we store for future use, and he was just reanalyzing this data and found a previously mysterious burst. This burst was very bright, 16 billion times brighter than our sun, and very short, as I mentioned, just a few milliseconds. So this picture shows Sparks telescope with which the discovery was made. It's a 64-meter radio telescope located in Australia, in western part of Australia. And on the bottom right, you see what a fast radio burst actually is in the scientific terms. So this is a diagram in terms of frequency and time of arrival of fast radio burst. And we see that it swaps a diagonal line in this plane, and I will explain later what it means actually. So this whitish line on the top of noisy background is the fast radio burst, and this is the first discovery ever made. So for some time, fast radio bursts were thought to be artificial and created by microwaves, because when you open and close microwave, it exactly creates short bursts of radio emission due to the magnetic fields inside. And our radio telescopes are actually extremely sensitive, and they can pick up microwaves far at the observatory. So since then, all microwaves are kind of arrested and placed in Faraday cages, which prevent leakage of this radiation and contamination of the telescopes. Such artificial bursts are called periton, and it's like a mythological animal, have deer, have eagle. So by now we know that our fast radio bursts are not peritons. They really exist, and they're of has cosmological origin. So why do we know that? It's because after the discovery by Parkes, we started discovering fast radio bursts with data telescopes from different locations on Earth. It took time for the field to evolve, and so I mentioned that the first one was discovered in 2001, but only in 2013 the next one was published. So it took 13 years to make another discovery. And in 2012, another fast radio burst was discovered by Arecibo telescope. This one was particularly interesting because that was the first one found to repeat. Due to repetitions of this event, people were able to localize the galaxy from which it is coming, study its properties, and accumulate statistics about the repetitions of this fast radio burst. Very rarely it is that we find fast radio bursts to repeat. In particular, the first one detected by Parkes, it has not been seen again. So today we know that fast radio bursts are detected by many telescopes around the world, and this is not a complete list of telescopes. There are hundreds of FRBs, about 100 published, and a few more hundreds in the pipelines. And some examples include CHIME, which I will be talking about today. And it's a cylindrical telescope which sees a large portion of the sky, so it collects collects fast radio bursts from a very wide angle. Unfortunately, it has poor angular resolution, so even though it sees a lot of fast radio bursts, they have around 300 in their pipeline. It's difficult for them to localize it, so they see an FRB coming from a general direction in the sky, but they don't know exactly from which galaxy. For them, it's also difficult to characterize the luminosity of these fast radio bursts. Another interesting telescope is ASCAP, and ASCAP is one of the most sensitive array of telescopes located in Australia. They have recently localized a non-repeating FRB because of their interferometry between different radio dishes. So they were adding up information from different telescopes and were able to localize a non-repeating FRB to a single galaxy located far away. So that was a very interesting discovery earlier this year, actually. And we already talked about Parkes, Arecibo. Some other examples include Green Bank Telescope in the US and Molonglo in Australia. Not necessarily dedicated scientific programs also contribute to the search of fast radio bursts, in particular SETI programs and SETI's search for extraterrestrial intelligence actually is searching in the exactly same wavelengths and for similar pulses that they hope are coming from other civilizations. In particular, Breakthrough Listen is one of the largest scientific programs that searches for extraterrestrial signals. They employ same telescopes that are used for science, but they bought out time on this telescope. And also they are searching a wide range of sky. They're very sensitive, so these telescopes can pick up a signal from aircraft located at one of the 1,000 nearest stars to us. So you can imagine how sensitive such telescopes are. So SETI search is very systematic, and if they find the fast radio bursts, they report them to the scientific community. They have found few of them, so it's an extra effort that is done towards understanding what fast radio bursts sound. If you are more interested in details, there is an open online catalog where all published fast radio bursts are listed, including the telescopes and properties of the pulses, how long it was, what was the brightness of this event, and so on. So I invite you to search online for this catalog, which is live and is always updated. So I mentioned that all fast radio bursts are different, and they are. So here's an example of a subset of known fast radio bursts, and we see that they all have this pulse, which is FRB itself, but details vary. For example, this one looks very different from its neighbor. And we are trying to characterize the entire population based on these very diverse events. It's a hard business, actually. And that's why we still don't know what their nature is. So I mentioned that we expect thousands of them, but we only found a few hundreds, and that's because until now, fast radio bursts were just found by chance. For example, Lorimer detected his first burst just searching through archival data. He didn't know about these things. So even though we weren't searching intentionally, we found 100 or so, and this means they are very frequent events on the sky. Now people are trying to do more coherent searches for fast radio bursts with surveys done on CHIME and ASCAP telescopes. And they are systematically scanning large portions of the sky to try to find more events. So I mentioned that we now know that they are astrophysical or cosmological, but how do we know that? Where are they actually coming from? Are they originated in our solar system, on Earth maybe, from our galaxy, or from distant universe? And given the information that we have collected so far, we know that they are mostly coming from far away, from other galaxies located many giga-light years away. So they travel huge distances from the time they are emitted to us when we can observe them. And the information that tells us how far these bursts travel actually is located in this diagram. So this simple line actually contains tons of information. By understanding how each frequency channel arrives in time and how the arrival time is delayed as a function of frequency, we can understand how far the burst was emitted. This is due to dispersion of fast radio bursts. And dispersion is a general property of light or radiation that propagates through medium. We know that white light that is shown on the prism will be dispersed, right? We often see a rainbow, even in a drop of water or around the waterfall we can see a rainbow, and that's because of the dispersion. And dispersion means that every frequency has different speed of propagation in medium. So even though all frequencies that make up white light have same speed in free air, once the light enters prism, every frequency has different propagation properties. So when the light goes out of the prism, we see the rainbow. And actually, properties of the material out of which the prism is made will also affect the result. So we will have different rainbows depending on different properties of the medium. And also the result depends on how long the path inside the material is, as well as on the properties. So same applies to radio pulse when it travels through ionized medium. We know that the space between galaxies actually is not empty. It's composed of gas. There is gas, but it's ionized. It's in the form of plasma, even though it's very rarefied. So when a pulse of radio emission goes through this ionized gas, it suffers same effect as light that goes through prism. Every frequency that composes this pulse has different propagation speed. Actually, shorter wavelengths, equivalent to purple light in the white beam, travel faster than longer wavelengths. And so if the pulse is emitted at the same time at the origin, every frequency will arrive at slightly different time to us. And so that's exactly what we see in this diagram. We see that every frequency has a different arrival time, right? So we can plot it. And actually from this diagram we can calculate how much dispersion the pulse has suffered, and from that calculate the amount of ionized medium between us and the source, and related to the cosmological distance between the source and the observers. So that's how we know that all observed fast radio bursts, they actually travel huge cosmological distances. So this is an integral a mathematical formula which allows us to calculate how far the FRBs were emitted, and it relates the column of ionized gas along the line of sight to what is called dispersion measure. And dispersion measure is exactly how dispersed the pulse is. For observed FRBs, the dispersion measure is between 266 to 2500 in the units of parsec per centimeter cubed. And if you make this calculation and extract distance out to the origin of FRB, it appears that fast radio bursts travel between 3 to 11 gigalight years. So they come from distant galaxies. Another evidence that the FRBs are coming from outside of our galaxy is that we can plot the location of fast radio bursts as a function of the sky coordinates that are called declination and right ascension. And we know that our galaxy takes particular coordinates in this space, so we would, if FRBs were coming from our galaxy, we would expect them to be aligned with the galactic plane. But that's not what we see. So each star here shows the location of each individual fast radio burst, and we see that this entire diagram is populated. So they're just coming from everywhere, not necessarily from our galaxy. And so based on the fact that fast radio bursts are coming from far away, we can actually use them as cosmological tracers. So this diagram shows the evolution of the universe from Big Bang to today. And there are different stages that the universe was going through on the way from Big Bang, when it was tiny and all located in a tiny patch, to the state that we see today with so many galaxies, cosmic web, planets and stars, and so on. So on this diagram, fast radio bursts are coming from the entire past 3 giga-years of cosmic history. And that means that we could use them to characterize galaxy formation and processes that were taking place at early times. And also we can use them to probe the medium between us and the source. So I was telling you about dispersion, but there are other probes such as rotation measure if the pulse is polarized, that tells us about the magnetic field in the medium between galaxies. And we can also probe the ionization state of the gas. So early on, at the dawn of star formation, the universe was still neutral. The medium between galaxies was neutral, and it was only then ionized by starlight. So fast radio bursts can give us a handle on all these events once we detect a large population, and we also know what they are actually. So we know that because we are far from the source of FRBs, we are actually detecting only a small portion of photons that are produced by the burst itself. So even though the FRBs are so far, the fact that we can see them today means that they are intrinsically super bright. They are much brighter than pulsars located in our galaxy, intrinsically. So both pulsars and FRBs have an intensity of 1 Jansky, the observed one, but the fact that FRBs are coming from much larger distances, 10 to the 6th time larger distances, means that they are 12 orders of magnitude brighter than pulsars themselves. So these are extremely bright events. And let's talk a bit about how we quantify their evolution of the luminosity with time. And we do it in terms of light curves. So in physics, we like to plot graphs and plots. Maybe you have noticed already. So this is another type of plot that we like to make. It shows luminosity as a function of time. For a source that is permanent, it would be just a fixed line, so luminosity doesn't vary with time. But for some sources such as supernovae or fast radio bursts, there will be dependence of the luminosity on time. So as time goes on, luminosity of the source will vary. So this type of plots are called light curves, and the different sources have different light curves. For example, our sun shows variability on the time scale of few years. We know that there are sometimes it's brighter, sometimes it's dimmer, so we can plot the light curve of the sun. It's periodic. For pulsars, we also can plot the light curves, and they show strict periodicity. They can be used because of that as probes of general relativity. Their variability is on the time scale of a few seconds. For sun, we saw it's on the time scale of a few years. Pulsars have a much shorter variability time scale. But this is also an example of periodic source. For supernovae, supernovae is a cataclysmic event. It's not a rotating star like for a pulsar. It's just an explosion of a star. It happens once in the lifetime of star. And therefore, it's not a periodic event. The light goes up at the explosion and then slowly decays as the supernovae expands. So this process also takes a few days, even years, and even centuries in some cases. For example, one of the oldest known supernovae is Tycho Brahe's supernovae. It has been detected in 1572. And we can still observe it today. So for this source, the variability timescale is several centuries. So for fast radio bursts now, we can understand this part of the plot. This shows light curve as a function of time, so intensity as a function of time. And it's non-periodic, so for most of the events it happens one time. It's very short and very bright. So it's nothing like pulsars, nothing like supernovae, and nothing like the sun. And if we compare the energy of the bursts, they're actually very bright, as I have already mentioned. So I did the rough calculation here. And the observed luminosity of fast radio burst is 10 times brighter than the sun, right? As bright as supernovae, but because of their duration, which is just milliseconds, total energy is still much smaller than that of the sun and of supernovae. But they can visually appear as bright, even though they're in radio. And so I told you about what we know about fast radio bursts, but we still don't know what they are. Their light curves are totally different from everything we observed so far. And there are many theories that are trying to identify fast radio bursts without success yet. There are many experiments that are trying to detect more of them and characterize their properties. Recently, ASCAP, that I have mentioned already, managed to localize a non-repeating FRB to be inside galaxies. So this is an example of galaxy located far away from us. And they were able to pinpoint the FRB to this black circle inside galaxy. So the yellow circle is galaxy, and the black circle in it is the location of fast radio bursts. So using other telescopes such as Dark Energy Survey, they were able to characterize properties of this particular galaxy, finding that it's early spiral type galaxy or lenticular galaxy. It doesn't form stars. Sorry. And it's very old. On the contrary, the other localized event was the repeater detected by Arecibo, and it was identified to be in a small metal poor young galaxy which was forming stars very actively. So far we have just two identified galaxies, and they look very different. So we don't know if the host the origin of FRBs is different in these two types of localized events, or they're the same and just the environment is different. So we don't know what the progenitors are, what makes the FRB. It's not a supernovae, it's not a pulsar, but what is it? And so there is a long list of open questions that we have to answer. And just to mention a bit about theories, by now there are around 50 theories that people propose. None of them works well for all the discovered events. Among the theories, there are neutron stars that rotate in highly magnetized medium, black holes, white dwarfs, and some exotic theories such as alien spacecrafts moving through space and reflecting emission. So I will stop here, and this is my conclusion. We have a new mystery to solve in astrophysics. It's very exciting. We still don't know the origin of fast radio bursts, and there are many open questions to discover with future efforts. Thank you.